So what we're looking at there, mutually exclusive means it's impossible for both of them to happen.
Okay.
So getting an A in stats and getting an A, I don't remember what the other one was, but let's just say in history.
Yep, that's what it was.
Okay. It is possible to do both. It might be difficult, but it is possible.
Okay.
So that means they are not mutually exclusive. In order for them to be mutually exclusive, the probability of the two of them happening together has to be exactly zero. It has to be completely impossible.
Okay. Okay.
So now the thought came up here in the chat room. They don't depend on each other. So are they independent? That's a good question. Well, that's actually a much more difficult question than mutually exclusive. Because you might make the claim, well, the student's intelligence level makes it more likely that they get an A in both. So, if you get an A in one, maybe they're more likely to get an A in the other just because they're a good student who puts in the time and all of that. So that's a little more difficult. To be independent, if one occurs, it does not change the probability that the other can occur. I would argue in this case that they are not independent because a student who gets an A in one class is most likely, more likely, more apt to get an A in other classes. Just because an A student tends to be a pattern of hard work and study habits and stuff like that. So I would say in this case, they're probably not independent. Okay, so any other questions?
Thank you.
You're very welcome. Okay, well, let's go ahead and start then with our new material for the night. We're continuing with probability, but we're going to focus on numerical random variables. Remember, the random variable is the answer to the question being asked. And in this case, whatever the question is, it's always generating an answer that's a number, numerical. And remember, we said our numerical random variables were divided into two categories: discrete, which are counted, or in other words, they're just set points along the interval. So we'll say isolated points along the number line. There's continuous. We said that was measured usually. And that is actually all values within an interval. So they could be, discrete might be the values 1, 2, 3, 4, 5, or 6. Continuous might be any value from 1 to 6. So it could be 1.7, 1.34, 2 to 6, 7, whatever. Anything, any value you can think of that's between those values, it can be that value. So let's take a look now. Tonight, we're going to focus mostly on discrete random variables. So variables can only take on specific values within a range. An example we might use would be a spinner. So let's say we have a spinner here. I'm going to do a little drawing. And in our spinner, we're divided into pretend these are equal slices here. And so we're divided into 8 equal slices. And these slices are labeled. Like that. So if we have a spinner, and by spinner, I mean literally like a spinner that it's mounted in the middle and can spin around. Make the different colors, it shows up better. So anyway, it's equally likely to fall on any of those slices, so any of those numbers. So using that classical and theoretical probability that we discussed the other day, we're going to let X be the value. So X here can be 1, 2, or 3. And P of X, the probability of that value. Well, there are 3 ones out of 8 on that spinner, or as a decimal, 0.375. There are 2 2s out of 8, so that'd be 0.25. 2 3s out of 8, so again 0.25. And I didn't get it typed, the probability of the 4, there's only 1 4 out of 8 for a probability of 0.125. Now, remember, we mentioned last week to be a valid probability distribution. First of all, each P of X must be between 0 and 1. All of those probabilities are between 0 and 1. Remember, probability of 0 meant it was impossible. Probability of 1 meant it was guaranteed. The total P of X, or the sum of the P of X, has to equal exactly 1. Well, over here, if we add these up, those do add up to exactly 1. So this is a valid probability distribution. So we can ask questions like, what is, let's do a probability of getting 3. Well, we just read that right off the table, 0.25. Those aren't very interesting. You're getting the probability of a single value you can just read out of the table. So what's the probability that X is less than or equal to 2? Well, this is less than or equal to 2 would be a 1 or a 2. So it's the probability of 1 plus the probability of 2, which would be the 0.375 plus the 0.25, which adds up to 0.625. We might look at the probability that X is less than 3. Now, at first glance, this looks like it's different than the second example, but it's not. It's actually the same. Being less than 3 would mean that 3 is not included. So this is still just the probability of 1 plus the probability of 2, or the 0.625. Subtly different is the probability that X is less than or equal to 3. The less than or equal to, now this does include the 3. So it's the probability of 1 plus the probability of 2 plus the probability of 3. So 0.375 plus 0.25 plus 0.25 equals 0.875 is that probability. Next, let's look at an alternative way we could have found number 4 there, the probability being less than or equal to 3. We'd use the complements. Remember, the complement is everything in the sample space that is not in the set, or the probability in this case. So the complement of X is less than or equal to 3 would be X is greater than 3. Well, in this set, the probability that X is greater than 3 is just going to be the probability that X is 4. That's the only value that's greater than 3 here. So the probability that X is greater than 4 is easy to find. We can just read that right out of the table. Because of the rules of complements, the probability that X is less than or equal to 3, or sorry, probability that X is greater than 3. Let me go back. Probability X is less than or equal to 3 is going to be equal to 1 minus the probability of its complement, 1 minus the probability of 4. So that's 1 minus the 0.125, which gives us the 0.875, exactly the same number that we calculated up above here. Now, in this case, it was only a little bit more work to go ahead and add all the probabilities together. There were only 3 of them. Where down here, we just found one probability and subtracted from one. But let's say there were 10 different values or even more. You know, the probability of being less than or equal to 9 would require adding up quite a few probabilities, where you could just do 1 minus the probability of being 10. And that using that complement could save us a lot of work. So when we're looking at our probability experiment or random experiment, we have to be able to define what the variable is within the experiment. For example, flipping a coin, the variable is just going to be the result of the coin, heads or tails. Well, that is not a numerical value. So we might look at the number of heads in 3 flips of the coin. That is now a numerical value, and it is discrete because we count the number of heads. So I see some stuff in the chat. Let me catch up on that. So our value here, values of X, so the terminology we're going to use is X is the value of the variable, and P of X is the value of its probability. So possible values of X, if our variable is the number of heads in 3 flips of a coin, well, here it actually could be 0, 1, 2, or 3. All 3 of them could be heads. So our P of X has to be calculated. Well, let's look at listing out the probabilities. Or list out the probabilities, list out the possible outcomes. Well, all 3 could be heads. We could have the first one tails, second one tails, or the last one tails for just one tail. For just one head, we could have the first one heads, the middle one heads, or the last one heads. Or we could have all 3 tails. Now, we saw a tool last week where we could have done this out using those tree diagrams if we wanted to. Tails, heads, tails, heads, and did the branches in the tree diagram, like we saw. But we'd end up with the same results. So remember the number of heads in 3 flips, 0 heads, there's only one that has 0 heads. 1 head, well, there are 3 in here that have 1 heads. 2 heads, there's 3 of them. And 3 heads, there's only 1. So let's fill in the rest of this table here. We have 1 that's all tails, there's 0 heads. 3 that's 1 head, 3 that's 2 heads, and 1 that's all 3 heads. So that is 1 out of 8, or 0.125. 3 out of 8, or 0.375. 3 out of 8, or again 0.375. And 3 out of 8 one more time, or 0.125. And again, those are all between 0 and 1, and the sum or the total is 1. So it's a valid probability distribution. Well, next I want to look at finding values of a distribution, mostly like the mean of a probability distribution. And we found the mean of a frequency distribution a couple weeks ago, where we had a table of values and their frequencies. Same type of thing is going to apply here. So we're going to look at the number of classes students are currently enrolled in. And let's say for the students that are part of our group, there's 1, 2, 3, 4, or 5 classes. If they're not enrolled in any classes, we're not considering them a student at the moment. And then nobody in our group had more than 5 classes. So the probability of that number, well, let's say the probability a randomly selected student is only taking 1 class was 0.1. 2 classes is 0.25. 3 classes is 0.35. 4 classes is 0.15, and 5 classes is 0.15. If I add those up, it will come out to be 1.0. So again, this is a valid probability distribution. Well, let's look at finding the mean. Just like in a frequency distribution where we took the value times the frequency, here we take the value times the probability. So up here, I'm going to do x times p of x. 1 times 0.1 is going to be 0.1. 2 times 0.25 is going to be 0.5. 3 times 0.35 is 1.05. 4 times 0.15 is 0.6. And 5 times 0.15 is 0.75. So there's our x times p of x. And we find the total of that. If we add those up, we get 3.00. The mean then is x times p of x, the sum of those, divided by the total probability, which is always 1. So we really don't have to divide by 1 because it's always going to be that. So just the sum of the x times p of x is our mean, or what we often call the expected value. So what that means is on average, if we repeat this over and over, the mean value will be 3.00. So the mean, if we randomly select students over and over and over again, record how many classes they're taking, and then at the end, we find the mean of all that, the mean would be 3. Well, let's look at finding the variance and standard deviation. To do that, we have to go a little bit further into the calculation. We have to do the value minus the mean. E of x is the expected value, or the mean. So this will be 1 minus 3 would be negative 2. 2 minus 3 would be negative 1. 3 minus 3 would be 0. 4 minus 3 would be 1, and 5 minus 3 would be 2. Our expected value of 3 gets subtracted from each of those. Next, we're going to square each of those differences. So negative 1 squared is 4. Negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. So we have those. And finally, before we add them up, we have to multiply them by their probability. So it's still that value is times the p of x. So here we've got 4 times 0.1 is going to be 0.4. That's the probability over there of 1. 1 times the probability of that row is 0.25. So 1 times 0.25 is 0.25. 0 times anything is going to be 0. This one, 1 times that probability is 0.15. And here it's 4 times 0.15, so that'll be 0.6. And now we have to add these up. If I add those up, I get 1.40. This is the variance. Now, of course, to find the standard deviation, we take the square root. So the square root of 1.4 is 1.18 approximately. That is our standard deviation. Now, when it comes to probabilities, the expected value is very useful. If you want to look at like expected incomes and stuff in a casino or things like that, the standard deviation and variance are important for letting you know how far you can vary before something has gone wrong in your system. But the expected value is actually quite useful in a lot of ways. So one of the applications of expected value is determining if you're running a fair game. So in a fair game where you cost money to play and then there's a possibility of winning money back, a fair game is a game where the expected value equals 0. So the amount that you expect to pay to play is exactly equal to the amount that you would expect to win on average coming back from that game. So let's look at a game here and we're asked, is this a fair game? So it costs $4 to play. The game, rolling a die. But you win. If you roll a 1, you win $0. You roll a 2, you'll win $0. Roll a 3, you'll win $0. A 4, again, $0. A 5, you win $6. A 6, you would win $18. So you roll a 1 through a 4, you get nothing. You've lost your $4 and you're done. You roll a 5, you get $6 back. So you're $2 ahead. You roll a 6, you get $18 back. So what we're going to do is we're going to multiply the probability of each of these times the expected winning. The X value here is the value on the die. Each one of them has a probability of 1/6. So for the 1, take the winning times the probability of that. So $0 times 1/6 is 0. Well, for rolling a 1, 2, 3, or 4, you're going to get $0 back. So your expected winnings is $0. For the 5, you expect you'd get $6 back, but you only have a 1/6 chance of rolling a 5. So $6 times 1/6 is $1. And for 6, you'd get $18 back, but you only got a 1 out of 6 chance of rolling an 18. So $18 times 1 out of 6 is $3. That sum total is $4. That's equal to what it cost to play the game. It costs $4 to play, and the expected winnings is $4. That would make this a fair game. The amount you expect to win on average is equal to what it costs to play. So a casino would not play this game because on average, they're going to break even, and they don't want that. They want a win. So a casino would adjust it so that this expected value of winning is lower than what it costs to play, so that they know that in the long run, they're going to make money. This is also how raffles and other fundraisers like that work. The payout has to be less than what it costs to play, what they're going to take in exchange for the right to play. So next we want to look at some specialized discrete probability distributions. There are a few of them out there. In this course, we tend to focus on one of them, and that is the binomial distribution. Binomial distribution requires certain conditions. This textbook doesn't necessarily talk about it, but it's something called Bernoulli trials. A Bernoulli trial has a few characteristics. One is there's only two possible outcomes. We label them success and failure. Now, that doesn't mean there's only two possible results. It just means the outcomes are grouped into those two events. Rolling a die could still be a Bernoulli trial if you classify rolling a 1 or a 2 as a success and everything else as a failure. The probability of success, which we're going to label with a small p, is constant. It never changes. So the chances of rolling a 1 or a 2 on a die never changes. It's the same no matter what. And the trials are independent. What that means is it doesn't matter. I could roll 3 1s in a row. The probability of rolling 1 on the next roll of the die is still 1 out of 6. The result of one trial does not affect the probabilities on the result of another trial. Another good one's flipping a coin. I can flip 12 heads in a row. The probability of flipping heads on the next flip of that coin is still 1 out of 2. There is no memory involved. It's still there. It's still the same chances. That's why a lot of people say, well, it's due. That's not true. The probability of success on the next trial is the same as it was on any other trials, no matter how many failures you've had in a row. So binomial experiment then is, first of all, n Bernoulli trials. So it's a set number, n is a set number. And x is the random variable that's equal to the number of successes out of those n trials. So again, let's look at rolling the coin, or rolling the die. Success is a 1 or a 2. Everything else is a failure. Probability of success, which is our little p, is 2 out of 6 or 1 out of 3. Let's say I'm going to roll the die 5 times. We could have 0 successes. So the values of x should be 0 success, 1 success, 2, 3, 4, or 5. All 5 of those rolls could be 1s or 2s. Well, to find the probability of each of those values occurring, a little bit more work to do here. So the formula, so probability that x equals a given value with n trials and probability of success equal to p is going to be equal to, first of all, we need to know how many different possible ways we can have the desired number of successes. So there's something called a combination. The combination uses factorial notation, like 4 with an exclamation point is 4 factorial. And that's just 4 times 3 times 2 times 1. So that would equal, what is that, 24. Well, a combination uses that. If I have a combination of 5 rolls taken 2 at a time, what that's saying is the number of ways I could have 2 successes out of 5 trials. Well, I start out with my 5 factorial divided by my 5 minus 2 factorial, and also divided by the 2 factorial. So looking at this, 5 factorial is 5 times 4 times 3 times 2 times 1. 5 minus 2 is 3 factorial, so it'll be 3 times 2 times 1. Times 2 factorial will be 2 times 1. So a lot of stuff cancels out here. The 3, 2, and 1 cancel out. 3, 2, and 1 cancel out up here. So on top, we've got 20 over 2, or just 10. There are 10 possible ways to get 2 successes out of 5 trials. To illustrate that, it could be the first 2 are successes followed by 3 failures. It could be a success, a failure, a success followed by 2 failures. Success, 2 failures, a success, and a failure. Like success, 3 failures and a success. A failure and 2 successes, and then 2 failures. And I think you're getting the point here. Those are the possible ways. I think I listed 10 there. I did. Those are the 10 possible ways to get 2 successes out of 5 trials. Well, a lot easier than typing these out is to just do the combination. And our calculator does this for us. If I go to the TI-84 calculator, I type in 5 trials. I hit the math button here. I go over to probability. So go to probability menu and notice option 3, NCR. That's the combination. I select that, and then I enter my number of successes, 2 successes. And there I get the 10 again. So there are 10 ways to get 2 successes out of 5 trials. So the formula, I move some stuff out of my way here. To get A successes out of N trials is N, choose A, times the probability of success to the power of the desired number of successes, so that's A, times the probability of failure, so that would be the complement of P, or just 1 minus P, to the power of the number of failures, so that'd just be N minus A. If there's N trials and A of them are successes, the rest are failures. So for this situation, this would be 5 choose 2 times 1/3 to the power of 2 times 1 minus 1/3 to the power of 5 minus 2. So let's go to the calculator and type that in. So the 5, math, probability, combination 2. Hit enter just so we're not confusing things in the calculator. So we got 10 times our 1/3. So 1 divided by 3, close the parentheses, to the power of 2, arrow out, times, my parentheses, 1 minus 1/3 to the power of 5 minus 2. And we get 0.3292. Well, with the help of the calculator, that wasn't horrible. But it was quite a bit of work and it was a lot to remember. Well, the calculator fortunately has built-in functions. Binom PDF is binomial probability distribution function. So binom PDF does exactly what we're looking at here. It is for the probability that X equals a single number. So let's show you how that function works in the calculator. If you have the TI-84 newer silver edition, TI-84 plus silver, you'll have something called the stats wizard. If you don't have that, well, then I'll show you how to get around it. But anyway, we need to go to our distribution. So it's second. Then you can see right here above the VARS key, it says DISTR. That stands for distribution. That's probability distributions. So we hit that key and it takes us to our distributions menu. Well, the binomial probabilities are down here Option A there is binom PDF. That's the one we want. And it brings up, this is called the stat wizard. It asks us how many trials. We were going to roll the die 5 times. Our p-value, our probability of success, was 1 out of 3, so 1 divided by 3. And our x value, we wanted 2 successes. We hit paste. It puts it into the function for us. We have to hit enter again to get the answer. And there we get the exact same answer. 0.3292 is that result. So that confirms the answer we calculated by hand. So that binom PDF function is very handy for finding individual values. But what if we want to find ranges like we did in our first example of our probability distribution? That's where binom CDF comes in. CDF stands for cumulative probability distribution function. So this is finding the probability that x is less than or equal to a value A. So if I want to know, let's just set up a different example here. So let's say here that we have 82% of students pass statistics on the first try. If a random sample of 15 students is selected, find the probability. Let's do probability of 11, exactly 11. Well, this is going to be a binom PDF. It's a single value. So let's go ahead and find that. So the calculator, second distribution. Binom PDF is option A. We have 15 trials. Each student that's randomly selected is a trial here. 15 trials. Probability of success, 82%. So that's 0.82. And we want to know the probability of getting 11 successes. There it gives us 0.1615 as that probability. Well, let's look at the probability of no more than 10 pass on the first. Let's say no more than 10 pass on the first try. So there's no more than 10. No more than 10, this is the probability that x is less than or equal to 10. If it said less than 10, it would be just strictly less than, but no more than would include the 10. This is where that binom CDF comes in. So I'm going to go to the calculator, second distributions, binom CDF. Notice everything looks the same here, only on top it says binom CDF instead of PDF. Our number of trials, well, there's still 15 students selected. P, probability of success, is still 0.82. Our X value goes up to 10. We want to know at most 10 or no more than 10. Hit paste and enter. We get 0.1167 if we round that to 4 decimal places.
Excuse me, Professor Hall.
Yes.
When I enter into the calculator, I get a syntax or go back option. So something's not right when I'm pressing it. I must be missing a step.
Okay. Let's see.
As soon as I press binom CDF, it gives me an open parentheses, and then there's a blank space behind that open parentheses.
Okay. So what you do not have the stat wizard is what it's saying.
Okay.
So if you do not have the stat wizard, what you do is this. It's binom PDF NPX. So what you would enter for this first one, it would have been binom PDF. I missed the F in that top one. Let me put that back in there. number of trials would be 15, probability of success is 0.82, and then X was our number of successes was 11. So you hit the binom PDF and it brings up that parentheses, do 15, comma, 0.82, comma, 11.
Okay. Do you know which way the book demonstrates it?
The book usually does use the calculator and Excel.
Oh, and does it assume that we have this newer calculator, or will it assume that we have the older version that we'll have to enter 15, comma, 0.8211?
You know, that's a good question. I have not looked that close to see it.
Okay.
I will have to look, I'll look that up for you and send you a message later. In fact, do me a favor, and after we're off here, send me an email reminding me to look that up.
Sure.
I'll make sure I get it back to you.
Okay, thank you.
You bet. And that is for binom PDF or CDF. That is the entry right there. Now on my calculator, I can turn, if you want to see how that works, I can turn the stat wizard off for a second. I go to catalog. It's going to take a while to get down to the S's. And I'll show you what this looks like if the stat wizard is not on your calculator. Okay, so I'm going to stat wizard off here. And this might be something to try on your calculator to see if maybe it just has been shut off on you. I'll show you how to turn it back on here in just a second. So I'm going to select stat wizard off. I have to select it, then I have to activate it. So now my stat wizard is shut off. So mine should look just like yours now when I go to binom PDF. So you go second distribution, binom PDF. So I'll select it and it takes me right to binom PDF with just the open parentheses. So N was 15 and then I hit this comma, 0.82, then I hit that comma again, and then I wanted 11 successes. Then I'll close my parentheses and hit enter. And there I do get the same 0.1615 that I did before. So something you may want to try just to see if you have this ability to turn this on your calculator, do second catalog. Then you're going to arrow all the way down. I'm going to see if I can't get a shortcut to get most of the way down there by doing Alpha S. It does not do that. So we just have to arrow all the way back down. All of the functions in your calculator are in this catalog. This catalog allows you to turn off and on certain settings. Many of them can be turned on in the menus. There's diagnostics off and on that are not in any of the menus, and the stat wizard off and on are definitely not in the menus. Most of the others are in the menus. I guess I should say the only two that I use that are not in the menus are the diagnostics and the stat wizard. So arrowed all the way down to the S's to get this, and these are alphabetical. So I select stat wizard on. Once it comes up on the screen, I have to hit enter one more time to activate it. Once it says done, then I know it's been done. It's turned on. So the next time I do a probability, I'm going to get that stat wizard again, which will help out. So the next example I want to do here, what about at least 10 pass on the first try? Well, this is the probability that X is greater than or equal to 10. This is the complement of probability X is less than 10. So the first question might be here, how do I know in the complement whether it's strictly less than or equal to? Well, that's a relatively easy answer. over here, there's an equal to here, so there cannot be an equal to in the complement. This is greater than or equal to, so the complement is strictly less than. So that means the probability that x is greater than or equal to 10 is equal to 1 minus the probability of the complement, that x is strictly less than 10. So I can use the binom CDF again, but being strictly less than 10, remember binom CDF was this up here, less than or equal to 10. It doesn't say strictly less than. So I have to adjust this. Because of the way the binom CDF works, it's going to be 1 minus probability that x is less than or equal to 9. Because this is a discrete distribution, probability that x is strictly less than 10 is equivalent to the probability that x is less than or equal to 9. Both of them are 0 through 9. 10 is not included in either one. This is the form I need it in so I can enter it in the calculator. So let's do that. So I have to do 1 minus before I go to my distributions. I do second distribution. Go to my binom CDF. 15 trials, probability of 0.82 of success. And I want to go up to 9. I'm subtracting out up to 9. Hit enter, and there I get 0.9613. That is my probability of at least 10. What if I want the probability that less than 10 pass on the first try? Well, this is probability that x is strictly less than 10. And we just saw I have to use probability x is less than or equal to 9 to calculate that. So this will be a little bit different than what we had up here for less than or equal to 10. So second distribution, normal or binom CDF. And actually, that's the one that's actually already posted in there. So we hit enter. And we get 0.0387 is that probability. And again, that makes sense that this probability should be less than this one. Now, the difference between those probabilities should be the probability that x is exactly 10, because that's the only thing that's different is the one up here includes the 10 and the one down here does not. So let's do that just to see what we get. Second distribution. We want the binom PDF this time. 15 trials, probability of success of 0.82. And we want to know 10 successes. We have 0.0779, 0.0780. If I were to add this to that, I do get exactly that probability. I'll let you add those on your own to double check that, but it works out. Those two add together to make that. So what if I want to know the probability of more than 10 do it on the first try? So this is slightly different than number 3 up there. This is the probability that x is greater than 10, which is the complement of x being less than or equal to 10. Since the equal to was not included over here, it has to be included in the complement. So this is actually easier. The probability that x is greater than 10 is going to be 1 minus the probability that x is less than or equal to 10. So we go to the calculator. 1 minus second distribution, binom CDF, 15 trials, 0.82 probability of success, and we're going up to 10. And we get 0.8833 is that probability. Now, once again, the difference between this one and this one up here should again be that. And I'll let you double check it, but it does work. This plus that would give us this probability. So as you can see here, the calculator, the binom PDF, which is just for individual probabilities in the calculator, and the binom CDF, which does that cumulative probability, are great tools for making these binomial calculations go very quickly. In fact, they do the calculations better than the tables, better than Excel. It's really is, the calculator really is the slickest way to do them. The biggest thing is you have to remember what to do. So let's say that we have probability that X is less than A. Well, that's just going to be binom CDF. Now I got to define my situation a little bit better here. So let's do this. Let's say that N equals 10, P equals 0.2. So the probability, and I'm just going to put a number in here then. Probability that X is less than 5 is just binom CDF. For 5, put in the 10 trials, probability of success of 0.2, and 5 successes. Oops, that should be probability X is less than or equal to 5. Sorry about that. Probability X is strictly less than 5. Well, that's equivalent to the probability that X is less than or equal to 4. So it's binom CDF, 10 trials, 0.2 probability of success, only going up to 4. So because it was strictly less than, we had to reduce the number by 1 to make it a less than or equal to. Probability X is greater than 5 is the complement of probability X is less than or equal to 5. Again, since this was strictly greater than, the equal to goes in the complement. So that's 1 minus binom CDF of 10 trials, 0.2 probability of success, and 5. Probability that X is greater than or equal to 5. Well, the complement there is 1 minus probability that X is strictly less than 5. So that's going to be 1 minus the probability that X is less than or equal to 4. So that'll go into the binom CDF as, oops, what happened there? 1 minus binom CDF, 10 trials, 0.2 probability of success, and 4. So there's a lot of different things that can happen here. These are the main ones. And of course, just the probability that X equals 5. This is the only one where it's going to be binom PDF instead of CDF. 10 trials, 0.2 probability of success, and 5 successes. This bottom one, pretty straightforward, pretty simple. The other ones, these 4, take some practice, take some patience to get used to. And there are 2 other possibilities. Let's say that we have probability that X is between 2 and 8. Notice the 2 and 8 are not included, not inclusive, or sometimes called exclusive. So those endpoints, those boundary values are not in it. So we're going to go from, basically this is going from 3 up to 7. So we're going to do the probability X is less than or equal to 7. Then we're going to subtract out the probability that X is less than or equal to 2. Because the 3 is in it, the 2 is the first value that's out of it. And we would use the binom CDF, 10.2 and 7. Finish that off and then subtract the binom CDF, 10.2 and 2. What if it was inclusive? So probability that 2 is less than or equal to X, which is less than or equal to 8. So this is what we would refer to as inclusive. The endpoints are part of the probability. Well, this is the probability that X is less than or equal to 8 minus the 2 is included, so we're only going up to the 1. So let's see, binom CDF, 10.2 probability up to 8 minus the binom CDF, 10.2 probability up to 1. Now, some might look at this and say, did we really need a binom CDF here if we're only going up to 1? Couldn't we have just done binom PDF of 1? The answer is no, because remember, the value could possibly be 0. There could be no successes. So by using the binom CDF there, we make sure we accounted for those other possibilities that could be less than the 1. So this, like I said, this here is really the big thing for this week, is figuring out how to manipulate that binom CDF function to make what the calculator is calculating match what the question is asking for. And it's really the difference between less than or equal to, and of course, greater than or equal to. So it's going to take some time. Be patient with yourself. And this page right here is one that you're going to want to refer back to. So I will leave this up right now for a minute. If anybody wants to take screenshots or cell phone pictures or whatever of this little page here. With that, does anybody have any questions?
I have a question about last week, but so I'll wait until,
Okay.
someone says they don't have a question about this week.
Sounds good. I'm going to move to a blank page here. Any other questions on this stuff? Okay, well, go ahead, Ricardo. What's your question?
My question is for page 189 on the book. It's question 39.
I'm going to have you read it for me.
Okay, let me pull it up here. I still have it up. Oh, did it time out on me? Let me see. I should be able to get to it pretty quickly.
Okay. Unfortunately, all they give me to use is the ebook as well, so I'd have to log in through Alex to get to the book.
Oh, I see. Yeah, no, I'm there now. I'm pulling it up here. So this is, it's one of those, if this, given that
Okay.
type of problem. Let's see here, ebook. Okay, I have it open. Go down to page 189. All right. So it has a chart and it says a fast food restaurant chain has 600 outlets in the United States. The following table categorizes them by city population size and location and presents the number of restaurants in each category. A restaurant is to be chosen at random from the 600 to test market a new menu.
Okay.
And then then the first question is given that the restaurant is located in a city with a population over 500,000, what is the probability that it is in the Northeast? So I was able to get the answer by chance one time, but I don't think I could consistently figure out the answer without first looking at the answer, then working my way back. But even when I, hit the answers for myself, I still had trouble figuring out what I was including and what I wasn't including.
So what we have here is the table is going to be something, and this might not look exactly like the table in the book, but It might be like 0 to 10,000, 10,001 to 100,000, and whatever those sizes are. One of them is going to be over 500,000 is the city size. And then somewhere along the other axis is going to be the region. Whether it's the southeast, southwest, north, northeast, all of that. Well, when it says given that it's over 500,000, that means we're only looking at this column that's 500,000. So we're not looking at all of the restaurants, we're only looking at the total for this column. And
Okay,
then find the probability that it's in the northeast. Well, we take northeast and we trace it over. And whatever number is right here, that's the number of restaurants that meet that requirement, that characteristic. So it's that number over the total for that column. Now, slightly different would be, what if it's given that it's in the northeast? Find the probability the city is over 500,000. Well, that'd be actually just the backwards of this. So now, given that it's in the northeast, that means we're only looking at this row that's the northeast. So now it's this total here that we're looking out of. So it's still this number here are the ones that are in the city of over 500,000, but it's now that number over this total to get the probability. So the given limits the size of your population. If there is no given, you're looking at this total, this grand total in the bottom corner here of everybody, of the whole population. But if there's a given, that means then we're focusing on just one of the row totals or column totals instead of that whole grand total anymore.
okay, so we would be focusing on the total of the given.
Yep.
So like the given of the northeast. Okay, that makes it a lot easier. Okay.
Okay. And that is that those conditional probabilities are kind of tricky to get used to the wording, because the wording is almost exactly backwards of what you would expect it to be.
Right, right.
Any other questions? Okay, well, if anything comes up this week, like I said, last week's starting probability is where we really shift gears and get into material that's new for a lot of people. So weeks 4 and 5 and coming up on 6 usually gets a little easier, but weeks 4 and 5 are where students start to struggle a bit. So please, if you have any questions, reach out to me right away and I'll get back to you as soon as I can. Otherwise, y'all have a great week and hopefully we'll see you here again next Monday.
All right, thank you.
You're very welcome.
Have a good night.
You too, thanks.
Thank you.
You're welcome.